Thank you all for coming and welcome to the Colloquium, which is organized by the Faculty of Computer Science of the Higher School of Economics. And I'm glad to introduce Alexander Panchenko, a professor in natural language processing at Skoltech. And today he will talk about neural entity linking. Alexander, please.
Thank you for introduction and thank you for your kind invitation to give a talk at your colloquium. My name is Alexander, and you can find more information about the research we do on natural language processing at Skoltech if you click on this link. And also you can find more information about my profile and my background on my homepage at Skoltech. So yeah, if you have any questions, feel free to interrupt me, preferably by voice. And if you have some follow-up questions, don't hesitate to drop me an email afterwards. All right. So the structure of our talk today will be like this. First, we will speak about motivation for neural entity linking. And then I'm going to introduce various architectures and the kind of a framework where the majority of existing approaches can be described. And then we're going to speak a bit about applications and how different approaches rank with one another. And finally make some conclusions, future directions of how this field of entity linking will be developing in the future. So my talk will be not really like deep in a sense that I'm going to dig into too much technical details, but rather broad to give you a better vision on what is going on now. If you want to dig deeper, you can refer to this survey article, which we released just about 1 month ago. This is actually, this entire talk actually is based on this survey, which was prepared with colleagues from Hamburg University and also MIT. So this overall talk is also based on a smaller version of a presentation by a PhD student from Hamburg, Özge. And yeah, I'm really glad that these contributions by my colleagues, they made this talk possible. Okay, so don't hesitate to look for this survey and maybe ask some more specific questions as we go. All right, let's start first with the notion of knowledge base. I'm not sure about the audience, but I guess many of you know about what knowledge base is, but still I'm going to describe a bit quickly what it is for those who might be not familiar. A knowledge base is the good examples of knowledge bases are Wikidata, DBpedia, Freebase. Well, now Freebase is discontinued, but it was this database was merged to Wikidata, and really it's a repository of entities and their relationships. You can have different records in this database, well, a database of knowledge. Let's say we have Douglas Adams, and you have certain identifier for every such kind of entity. This is like technically important because these identifiers usually language independent. So whether you have an article or a record in such a knowledge base about Douglas Adams in Russian or in English and in German, usually this identifier is going to be the same. And in fact, this is an extremely powerful feature which enables various applications. And this is how DBpedia and Wikidata and other knowledge bases are organized. And well, what you can have in this repository, you have some certain description of this entity, maybe definition of this as an English writer, humorist. And then you have like a list of properties or attributes of the entity. Let's say Douglas Adams was educated at St. John's College. And these lists may be actually very long, but and St. John's College in this case is kind of a value of certain property. So this is how it looks like for a human being. Then you open Wikidata or DBpedia and look at these objects. Now, a bit more formally, a knowledge base can be represented as a multi-label graph where you have usually nodes and edges, like a tuple of nodes and edges in this graph. And the nodes of this graph are entities like Douglas Adams or Moscow City or High School of Economics. And the entities are interconnected, so the edges can be represented as a dot product. A Cartesian product of three sets: a set of entities to the set of entity types to the set of entities. Well, this is so because usually in the knowledge base you not only have links, like a directed links, like in a graph, but you have like multiple types of these links. Recall the previous slide. So you had educated at attribute. Well, you can have educated at, you can have attribute born in, and so on and so forth. So these will form these unique types of relations. They will form this set. And entities themselves, they form set E. Very often, you can consider if a knowledge base is based on Wikipedia, such as DBpedia or Wikidata. So you can think of one article in this encyclopedia as one entity. There are some restrictions, like there are navigational articles, disambiguational articles, and so on and so forth. So they are basically purely functional, purely technical, so they usually don't count. But other than that, usually you consider one article, one content, which article as such kind of entity. Well, I'm not sure about exact numbers, but let's say English Wikipedia contains maybe 7 million of articles, something on this range. The number is always growing. And the number of types of relations, usually it's several hundreds of relations. So this is a kind of amount of data we're speaking of. And of course, this all multiplies by all these hundreds of languages supported by Wikipedia. And like an element in this knowledge base, in this structure, is usually a triple. Often it's called SPO triple for subject, predicate, object. So this terminology is very common in the knowledge base, entity linking, semantic web communities. So it's worth knowing it. And the predicate is really just like the type of this relation. And as you see, this triple, you can represent it like this as well. So you have, because you have these triples, you can also represent every knowledge base as a kind of three-dimensional tensor. So you have dimensionality being equal to the number of entities, and then to the number of distant relation types, and then to the number of entities. So this kind of a cube where a point in this cube is a presence of certain relations. Let's say Scott Young was educated at Cambridge. And so then this will be one point of information in this knowledge base. And so this duality is very useful, obviously, because you can operate and apply different approaches to both representations. All right, but here is just a small example of this a small part, very small part, a local ego network of San Francisco entity. And you can see that, okay, San Francisco in Wikidata has this fancy identifier Q64, and then it relates to other entities. So San Francisco has mayor, and then it has certain identifier, and then location, and so on and so forth, certain population. And then, okay, in this figure, we represent this. They represent these attributes with scalar values with these boxes, but in principle, there is no difference between a triple which relates one entity to another entity with certain type, and one entity linking to certain value, like a string or integer value. So this is also actually a triple. So in fact, yes, everything in these kind of knowledge graphs and these formalisms can be represented as triples. Now the question is that this object might be another entity, and then according to this in this figure, you would represent it as a string, as a line, but it can be just a value, and then you can represent like this. And okay, but why would you care about these knowledge bases? This is because they allow you ways to build applications for very complex semantic processing. Let's say you want to build a search engine which is able to retrieve mentions of during the last month of all retired NBA players with a net income more than $1 billion US. So, or maybe you can do search engine which is able to do some other kind of searches like this, which allow to the user to do this kind of complex searches. Well, the list of the players together with their income values is available in Wikidata. So you know that Michael Jordan is a retired NBA player. And then you have an certain attribute saying what is his net income? Well, it's such and such number is more than $1 billion US, or something like this. So you actually can gather the list of persons you want to search in this news collection, and then it seems to be very easy to accomplish the task. You just need to grab through this news corpora and count the numbers, and you're done. But it's not as easy as that because of the main issue in text processing, which is ambiguity. Ambiguity can be found on basically all levels of linguistic processing, and in this case, this is a lexical ambiguity. As you know, you have Jaguar car, Jaguar animal, Python programming language, Python snake, and the same thing happens here. You have Michael Jordan basketball player, but then you have this long list of other Michael Jordans, like Michael Jordan, computer scientist, who invented or proposed LDA, and no names, Michael Jordan's, writers, whatever. So it is a problem if you want to do this exact counting. And this is really where entity linking come into play. So you're going to solve this issue. So really, the problem entity linking tackles is to provide a link from a textual content to this knowledge base, to this structured information. So you go into link information in unstructured text data source to a structured data source, which is knowledge base. And during the process, usually what happens is you are going to match a mention such as Michael Jordan as found as a part of certain article in this textual context. So you have this particular news article, and you are going to link this mention to a specific entity in the knowledge base, which is unambiguous. So which says that, this is a Q64, and the Q64 refers to basketball player, period. So this is, and there may be another entity in this knowledge base, which, 164, and that one represents basketball mathematician. So this is really the key technology to do these kind of semantic processing applications. And let me just illustrate you how it can be used to further motivate it. One common task is a question, knowledge-based question answering. Think of this question like how old Trump is, and there is a definitive answer to this question for a given point of moment. This is 74 years old. And, by showing this card, basically you completely fulfill information need of the user. You don't, once she gets this answer, there is no need to further even read anything. And the most important information on the slide is this line that Wikipedia article contains this attribute, this relation was born in, with the indication of the date, exact date. So once you basically get this link, like the fact that Trump is not a trumpet, not anything, but it is really the president of the United States, like ex-president of the United States, and then you are able to just look up this feature and answer. So fantastic. Is another example by similar functionality by Google. So the question was which country Tahiti island belong to, and actually correct answer is France. The answer which is provided by Google is French Polynesia. It's like geographical part where Tahiti belongs to. But anyways, you see that Tahiti as there is information about Tahiti, and inside this thing you will find, in fact, a country, so attribute which would give you the answer to the question. And Wikipedia is not exactly the same as Wikidata. It's a basically a resource which is intended to be human readable, but really the idea of Wikidata and Wikipedia is to extricate information from this man-crafted encyclopedia to make it structured. So basically the majority of information available in these Wikipedia pages is available in Wikipedia bases, knowledge bases as well. All right. And here's just a small structure of a sketch of algorithm, how this can be addressed, how this can be implemented. In the Pablo framework, there is an implementation for this KBQI or Wikidata, and it works like this. First, there is certain identification of query type, because you just can want to make sure what kind of question user is answering, trying to ask. And the second step is to detect entities in the query. So how old is Trump? What do you want to get? You want to detect Trump mention. And then really the core is to, the core step is to get a link to knowledge base to further generate a set of candidates. So this is how entity linking is used in this context, in this scenario. Once you got the link, then you can get the relations and rank them further and generate the answer, but we are not really speaking about KBQI today. But really my point here is that without entity linking, you would not be able to proceed really much to solve this KBQI thing. So entity linking is a useful thing. Okay, so there was just an introductory part to convince you that entity linking is a good thing to do. If you have any questions, really feel free to interrupt me. Otherwise, I proceed. Okay, so a little bit more formally, entity linking looks like this. As an input, you're obtaining some plain text like this one. What usually happens, mentions of various entities are recognized. You see here them, they are in a bold font. And then each of such kind of entities is going to be disambiguated with respect to a set of reference, senses, if you want, of these different mentions. The output is going to be this set of links or two corresponding to entities. So we're going to enrich the input text with these various hyperlinks. So you have these contexts and you generate the mentions, and then this indentation, so that for each mention and a context pair, you're going to produce with entity disambiguation thing a link to the entity. Right. And the interesting thing is that the majority of neural entity linking systems can be described using this schema. So they work like this. You have, as I described on the previous slide, some text. Then you recognize the mentions. And then what's going to happen is that you're going to generate for each mention a set of candidates first. Like candidates like Scott Young. If you have this Scott Young mentioned, you're going to retrieve or fetch a list of all various Scott Young's politician and then football player, so on and so forth. Then these candidates mention and context, they are going to be vectorized. They are going to be represented in some vector space. And then these vectorized representations are going to be ranked according to certain criteria. So you have certain score according to each, which correspond to each candidate. And then you will get You will pick usually the best one or none if there were no good candidates or something like this. I will speak about this later. And let's take a look a bit more in detail on these 4 different stages. The first one is candidate generation, then mention context encoding, and entity encoding, entity ranking. So these are basically 4 pillars of neural entity linking. If we speak of classical approaches, which were based on well, classical machine learning, where you usually would have to design features for your models, and then the models usually going to be linear, some simple low variation models. So they could be basically more variations, but the more recent models, neural models, they're going to usually to fall into these 4 steps. The first step is candidate generation, and candidate generation can be represented as a function which takes a mention and gives you a list of entities. So this is like on the previous slide. Now, 3 common approaches to do this, and they are very heuristic, but they work, in fact, quite well. First is just to use surface matching. You get this big blue mention in the text somewhere. You get this big blue, and then you have a list of 7 million articles on Wikipedia. Every article has a title, and then you just loop through, or hopefully not loop through, but design some optimal data structure. But this isn't the point. You're going to check how similar this big blue is to each of the titles. If you have certain article which exactly corresponds to the mention, well, that's great. That's probably the best candidate. If you have an article which is quite short, article title which is quite short, and the large fraction of this title is exactly the mention, well, it's probably also a good one, and so on and so forth. Right. So you have some examples of this retrieval here. So you have IBM Big Blue disambiguation navigational page, but also all other kind of Big Blue articles. Another approach is based on the dictionary lookup. This is just to retrieve, to use disambiguation pages or means redirects to get this list accomplished. And the final one is a computation of prior probabilities of hyperlinks. This one is so very straightforward. What you do in this approach, you get a bunch of texts which are all labeled, which all contain hyperlinks. You can start with Wikipedia, and in Wikipedia you have links to internal links to other Wikipedia articles. So then what you do, you just take a text of the hyperlink, you save it, and then you also take the link itself. And then you just compute these prior probabilities. Given this mention, how likely is that this mention is going to lead to certain page? Let's say if I see Trump, probably the most likely link will be Donald Trump, as Donald Trump is a very popular person. He was the president of the United States, and there are a lot of mentions of this person. And maybe there are many other Trumps, but there will be less number of links to these in the text, so probability will be low. And in this approach, you see that the desired IBM, in fact, is also present. So it's a very powerful approach. Why I'm actually speaking so long about this approach? This is so heuristic. Well, people from Google, they released this cross-wikis resource, which was built from the web, and it worked in exactly the same way I just described. So they got the web, and they just counted, this, well, with some smoothing and some stuff like that, but they just counted the number of times given string you get a certain link. It turns out that this is a very strong baseline, very hard to beat, and in many following papers, people shown that the role of candidate generation is extremely strong. If you are able to generate good candidates, you are able to provide good results. And improvements of all subsequent steps, they're actually not really marginal, but they are not like dramatic. This is a very interesting observation, and in fact the explanation why this happens is because of the dominant senses. So these probabilities represent dominant senses of entities, and following research in word sense disambiguation, a very strong baseline is most frequent sense baseline. Let's say the most frequent sense baseline of Python is a programming language, and no matter what occurrence you have, if you just say, okay, this is always programming language, like most frequent class is the data. If your data are extremely imbalanced, most frequent class is a very strong baseline. Now the language data, linguistic data, they're almost always, due to zip flow, extremely imbalanced. So you have this exponential distribution of occurrences and frequencies and stuff like that, and that's why this works so well. Another reason why you should think about candidate generation is that instead of all of these fancy neural things, the candidate generation is still, in the majority of the models, is just separated from the pipeline. So you have all of these complex neural networks, but in the majority of the cases, candidate generation is still taken from this dictionary of probabilities, which is probably will be addressed at some point and addressed by some models, but still it's dominant thing to do. All right. So yeah, the second step, the second part of this architecture is a context mention encoder. Context mention encoder is taking a pair of candidate dimension and is going to output a vector representation of this mention. So you have Python as a programming language in certain sentence. This thing is going to encode Python depending on the context where it appeared. Should be very familiar to you in terms of contextualized embeddings and things like that. And indeed, the way to perform this encoding, well, originally it was done using such architecture as CNN and RNNs, but also recently pre-trained models such as BERT and Elmo and whatnot. They are used to perform this encoding. So this is usually based on some neural model, which is bidirectional and which takes into account information from left and right context, vectors from left and right context, and information about the given target, the given mention, making use of some usually large pre-trained language model, such as BERT. Okay, so this part is clear. Then another important component is entity encoder. And entity encoder is representing in the vector form all of these candidates, which are fetched by candidate generator. If you have this set of candidates, well, you want to have not just a list of Wikipedia identifiers like Q64 and so on and so forth, but you want to have a list of low dimensional vectors so you can work with them. And this is exactly the goal of entity encoder. The tricky part with this is that you usually have a very large number of entities. These might be numbers like 10 million or 20 million, sometimes 100 million. In commercial knowledge bases, you reach billions of entities. And the number of training examples is usually very small, and exponentially is very skewed in terms of distribution. So similar to the language models, pre-trained language models used to perform this mention context encoding, really you need some kind of a pre-training for entity encoding as well. As if you have some, John Smith Capetner from Louisiana, you might have even like Wikipedia entry about him, but maybe no mentions in the text. So it will not be possible to just easily pre-train them. So slightly different methods are used. So here's just visualization how entity embeddings and entity representations might look like. So you have Scott Young as a mention, and then a good pre-trained representation is going to create certain topology of these entities. Originally you have 5-7 million of entities, and this is just a flat list. Now what entity representation does, it's going to introduce certain topology of in this list, so that semantically similar entities will be close together in this space, and semantically distant entities will be distant in this space. This is very similar to word2vec, but really in some other distribution models, really the difference is that you deal not with words, you deal with entities of a knowledge base. And yeah, there are different ways to learn these representations. One simple, straightforward one, you can get some text associated to each entity and use some pre-trained or unpre-trained text encoder to project these texts and to use this textual information to learn the representation. Every article has a certain definition of this entity, and this is very powerful training data for doing this. Otherwise, you can use a structural information which links these different entities. One element of the graph is related to another one through many links, and you can use something like graph embedding approaches to learn these representations. There are other types of data you can use to learn these entity representations, such as word entity co-occurrences and so on and so forth. So usually you are going to deal with some kind of a variation of a word-to-vec model operated on whether text or a graph. So, and a modification of word-to-vec graphs called not-to-vec or deep-vec, they work almost the same. So, yeah.
May I ask a question?
Absolutely.
Yeah. Hi, Alexander. Yeah. So, can you please go back to the previous slide? You state here that each unique entity has its own low-rank, lower-dimensional dense representation, right? And then we basically have many different entities, and we have different relations, different types of relations. And I would assume that even if we consider the same entity, when we also take into account different types of relations, the embedding for this entity can be ambiguous. I mean that the way, let me think of the example. Let's say the person runs and the program runs are completely different things, right? The program can be an entity and the person can be an entity. Run is the same type of relation, right? But in the case of person, it means one thing, and in the case of the program, it means another thing. And then
it might be well. I'm not sure about the run, but I think in this case,
yeah, well, maybe it's not the best
different
example.
relations as well. So relations, they are supposed to be, I think, unambiguous as well. So if you have for something like run, like in the sense of execution of computer program, and the run in the sense of a jogging, I think in a knowledge base, you are going to have two different relations for this. So.
Okay, so the ambiguity is resolved by having different representations for the type of relations, but not for the entities themselves. Okay.
But the entities,
yeah, probably it solves the problem.
Yeah, so you have hundreds, maybe thousands of these different types of relations. In fact, they have many even duplicates because these types are created by humans. So some guy might create is a relation, some guy might create part of relation, and maybe somebody did not collapse them. But entities are unambiguous, and relations themselves, they are supposed to be unambiguous, I think, as well. They're supposed to be. I mean, this is the real data. The real data is like always noisy, especially if the real data entered by humans somewhere in the machine, right? But
sure.
You know, in theory, should not be ambiguous. Okay.
Yeah, that's actually a very interesting question. But you're not aware of any kind of analysis that would sort of look at this problem of ambiguity in the relations, or disambiguation of the relations, not of the entities, in an automated way. Like you said that you just said that typically that some person who populates the information in the database, in the knowledge base, you sort of assume that the person does a good job in distinguishing between different types of relations, even if they are similar from the linguistic perspective, like in the examples with the run. But is there any work on disambiguation of the type of relations?
Yeah,
not the entities.
Disambiguation of type of relations in which context? Because in context of the use of certain relation, or where? I mean, how do you define this task disambiguation of relation?
Yeah. Maybe another example will help. So I'm thinking about the algebraics of the slower dimensional representations, and I would expect that let's say if we compute the scalar product or some other type of linear algebraic operation, perform some other type of linear algebraic operation on the entity with the type of relation, like in a word-to-vec model, right? We can like sum two words, and then we will get another third word, right?
Yeah.
I'm thinking, I'm thinking in a similar way here. We have an entity and we have a relation. Then, if we do some algebraic operation on both of them,
there is a very famous paper by Marco Baroni called that nouns are vectors and adjectives are matrices. So you have a red moon, and moon is a kind of a matrix, and then you multiply I don't know, tree or car by matrix for red, and then you have some kind of rotation, this and yeah, I mean, this is one of the ways to think of relations. There are the graph embedding approaches. Sometimes they just use offsets and simpler models, but yeah, I think it's very practical to have a relation, vectors of relations, but in the context of entity linking, it's I think a bit less crucial, because relations actually used very indirectly. So actually, yeah, the point where relations are really used is only here, for entity encoding. So the majority of approaches, they use annotated text, in fact, so they don't use these links directly even, but some approaches use graph of links to run something like a not2vec, on the GIS graph, and then you have embeddings. Let's say we got some prior experiment with Özge. I'm not sure whether it's listed here or not, and we got a graph of hyperlinks, and then we run deep work on this graph, and we concatenated this representation with representations of something like not2vec, and it got some improvements. But yeah, if you just other than that, in entity linking, relations, they are not as directly used, so it's more like a motivation. If you link to this information, you can do fancy stuff with these relations. You can do some inference, but to perform the linking itself, you need the links when you want to encode entity representations. You should pre-train entity representations. Yeah.
Okay, so maybe we better proceed. And
okay, yeah, we better proceed because
thanks.
but thanks. We discuss. Thanks for the question. So, okay, the another important component of this is entity ranking. Entity ranking it works like this. So you have a list of entities, entity candidates, a context, and a mention. And you want to produce a score which characterizes the fitness of this particular mention in this particular context with one of these candidates. So in this context, writer is much less fit than maybe American or professional football player. So as this is how all these different encoders fit together, so you have this context mention encoder, which uses pre-trained language models such as BERT and stuff like this. It gives you a vector representation of a mention. Then you have entity encoder, which uses pre-trained representation of entities, and it looks up these entity vectors, and then a certain similarity between these two is computed, usually through some non-linear transformation, taking these vector presentations as input. But the simplest approach might be to do some transformation from one space to another, and then just to compute cosine similarity or some other similarity function, just a dot product, and say, okay, in the rank the mentions like this, so the rank candidates like this, and then the linking is happening just by picking the most confident, the most similar pair of mention and entity. There are other approaches you can use. They would perform more explicitly some machine learning, you can have a set of target mentions and true candidates, and then you can have some random candidates which does not fit this context, and then you can formulate it as some kind of standard negative loss likelihood objective, and to perform this kind of a classification. Okay, given this context and given this, whether you're going to predict one for compatible candidate with a context and 0 for a random candidate in context. So this is very similar to watermark objective. Also, people investigated ranking losses where you don't use this binary classification framework, but you rather try learning to rank thing, but it also works. Okay. And final ingredient to the general architecture is a nil prediction, and the nil prediction is some kind of a reject option. So think of, you speak of a person who is not listed in the knowledge base. There is no good solution to this linking problem. You have to reject to link this, otherwise you will be forced to make an error. And therefore, a nil prediction is taken, a context and mention, and then just the knowledge base, right? And all possible candidates in the knowledge base, or candidate list in the knowledge base, and you are trying to say, okay, it makes sense to link or does make sense to link. So a reject option is the last thing. Okay. Now I quickly go through different modifications of this framework of this general architecture. One important one is when you don't do these steps separately. You go in to get a context, just the text, no labeling, nothing, and then you go in to produce a list of mentions with the given positions and entities. This is usually treated where you go in to generate candidates from every n-gram in the text for every span, and then with some heuristic filtering, let's say you want to pick noun phrases, and probably you don't want to pick some determiners, something like that. You go in to do all these other steps we just discussed. So why joint entity linking is hard is obviously because an error will be propagated if entity recognition phase failed. There is no way the best entity disaggregation in the world going to solve it. Joint entity disaggregation in itself is a more hard thing to do, but because these tasks are interrelated, you can try to optimize them jointly and obtain better scores than the models which do this completely separately. So this is a very good thing to do, to try to do things jointly. Another modification is global context architectures, and the idea is illustrated on this figure. You have a text as input, and in this text, 3 mentions were detected: Wales, John Hudson, and Scott Young. If you use the framework we just described, what you're going to do, you go to solve them one by one, and the order wouldn't really matter, right? So global architectures take into consideration the fact that different candidates for different mentions contain they are semantically related. So Scott Young, as American football player, is related to maybe Wales team, and less related or unrelated to Wales UK. And George Hudson, Welsh football player, related to George Hudson, Scott Young, and so on and so forth. So if you correctly identified one of the links, this information is very useful for distribution of other types. It's basically because you have some topic or like a Latin variable which would go into encode a certain theme of the document. If you speak about football, it's likely that all the entities, they will be related to this football theme, and if you want to get like a dense subgraph from all of these candidates, you don't want to get you want to get basically a coherent solution. And this is what global context architectures trying to do. They try to take into account the similarities. So in local context, we do this one by one. In global context, we take all dimensions in the context, which is document, and solve this in one shot. Then the problem is that the more entity dimensions you have, the longer document you have, the more computational complexity you have. So this starts to be combinatorial. That might be a problem, not very practical way to do it. And that's why some solutions, they rely on some just pairwise entity scores and just integrate them into some kind of a local system, or integrate prior solutions, prior decisions, let's say with some sequential models such as LSTM or CRF, right? So you was going for the document and you made some decisions, and then you know what entities were disambiguated, or this information is somehow implicitly encoded into some vector representation, and it's going to influence your future predictions. But trying to do this hard combinatorial problem might be problematic. Okay, some other twist of all of these indeed linking things. The approach is based not depending on the domain, and really the issue is that many entities does not contain much training data. So you have usually a very skewed distribution, some kind of a Zipf distribution of mentions of occurrences of this entity syntax. So you have lots of mentions for Trump and for Obama, for whatever popular personage, but not for the majority, 95% of the data. And that's why you want to do some kind of zero-shot approaches. So new entity goes in, can you do something about it? Entity with no data comes in, can you still link it or not? That's these approaches, they called zero-shot. Usually the setting of zero-shot, you have a new entity with a description, and that's it. And then you have to say whether this context is compatible with this entity or not. This is one of the recent trends in neural entity linking. So zero-shot approaches, they rely on some retrieval similarity computations, and they use some pre-trained ranker. As you see, the ranker itself is just taking some candidates and some contexts, but there is no link to a particular entity identifiers, so they just operate with vector representation. So in fact, you can use this combination of things to try to perform zero-shot linking. And of course, some pre-training always helps. Right. So the last branch and the way for modifications, the approaches which try to go cross-lingual. So you have a text entity link in Russian problem, but you have a perfect entity linker for English. Well, how to do about this if you don't have so much training data? Usually these cross-lingual entity links go into the rescue because you have a lot of in common and representation of entities. They are common for all languages. The only thing you need to add to this picture is some language-specific context mention encoder, which will be compatible once you have this. And we now see a boom of creation various models like this, like XLMR and multilingual BERT. So then you can try to think of some kind of cross-lingual neural entity linking thing as well. Yeah. Okay, so for the sake of time, I'm just going to click through. And so this figure just shows the various combinations of architectures. You see many different models have completely different design choices. Some models use CNNs for encoders, CNNs with tensor networks, attention-based models, recurrent models, feed-forward networks, and so on and so forth. Some models are global, so many people try to use this feature in some sense. The majority of the models are focusing on disambiguation, so they actually don't do this first step. They just assuming, the end dimensions are given. And entity embeddings which are used, well, there is the majority are using some pre-trained embeddings. Candidate generation, different models again use completely different things. So you see the heterogeneity of the approaches. If are large, or a few approaches are cross-lingual, or very few approaches are zero-shot. But this is emerging trend. Okay, so now I'm try to go quickly through different ways how you can use.
So I think we have like 5 more minutes.
Yeah, sure.
Approximately.
Okay. So the classical approach to use anti-linking is to apply it into semantic applications such as biomedical and relation extraction. But also you can use applications like I shown in the beginning of my presentation, like semantic parsing, question answering. So this is a big thing. But recently what has been proposed as well is to integrate objective of entity linking and entity linking preprocessing into some neural model. Because neural entity linking is a neural network, you can add this into objective function of some other models. And through this multitasking, semantify your model and make it work better. Let's say no BERT would go into extend BERT with which would have these two components, so masked language model and next prediction, with the third component, which is going to integrate entity linking in itself, and this would be, improve the quality of the language model itself. So this is a very interesting direction, and other people also tried it, try to integrate into language models different things are outputted by entity linker, and it actually improves things. Regarding how you can evaluate entity linking, there are two big directions. So this is entity disambiguation. So you're given a text with mentions, you have to link them, and end-to-end thing, then you just get through text and you have to entity link them. There are a bunch of data sets you can use to do this. The most common is AIDA. And these data sets can be used in various settings, but usually they're used for entity disambiguation. Here is just important figure showing that classical models, they are way far behind neural entity linking models, and this is why we are having this talk today, because the quality over this decade improved by more than 15 points. So it really makes sense to use neural entity linking. Let me just focus on the fact that the evaluation itself is very sparse. So if you take these different data sets, you see that, yeah, most people evaluate something on AIDA, but other than that, the other data sets, they are used from time to time. So if you need one data set, pick AIDA. I'm going to maybe say also that end-to-end evaluation is much more rare. There are much less end-to-end systems and much less results. The previous big table was for disambiguation if you take entity evaluation, it's very rare. So of course you can use application-based evaluation. That's great. You can also evaluate separate components such as entity evaluation, like it was done in some studies. And okay, let me summarize. So entity linking, the methods based on neural networks performs much better than classical entity linking methods. Entity linking methods based on neural networks can be summarized with four main components: candidate generation, mission, entity encoding, and candidate ranking. And there are a few main modifications, branches of modifications, which you can list, which are addition to this architecture. And yeah, future directions, it makes sense to get rid of the candidate generation step, which is currently like dictionary based or non-neural, not end-to-end, and integrate more zero-shot approaches, and also further develop this direction with integration of entity linking as a neural network into some other neural networks. This already shown very promising results for neural language models, but I believe that it can have more potential. Okay, so thank you very much for attention, and I guess now we can get to more questions.
Hey, Alexander, thank you very much for the talk. And we have some time for questions, so please feel free to ask them.
I have another question regarding the evaluation. Am I understanding correctly that evaluation is more or less standardized in this field, right? So it's not like everyone picks whatever, like for example, if you have a data set with some entities and relations between them, you can select randomly the test data, right? And then if everyone runs different subsamples of the same data, then they will probably they can probably show different performance, right? So the same algorithm that are run on different subsamples will behave differently, and we can switch their places in the ranking of who is the best. So what is the situation with the evaluation in the field? Is it fixed, and who decides which test
so
data
if we speak of AIDA and entity disambiguation, so AIDA is the largest data set, one of the largest data set, but it's very commonly used. Then yes, AIDA has different splits, which are train, test, development, and there is no problem to follow this setting and get some reproducible and compatible numbers. One thing which detail which I didn't have time to discuss is the list of candidates. The candidates greatly influence performance, and if you fix them, you probably will be more scientifically correct in the sense, because that might make all the difference, not another neural network used for ranking. So if for to be good, you want to make sure what list of candidates you use is it the same list of candidates used in some other models. So say you have neural network 1 and it performs ranking, and then you want to test your approach. Well, first of all, fix set of candidates, and then, yeah, of course, do it on the right splits and stuff like that. But it's more or less standardized. There are even frameworks, software systems, one called Gerbil. It's like a big web service which integrates dozens of data sets like this. You can perform different metric computations. It's a bit wacky, but yeah, it can get you all the baselines in one place and all the numbers, and yeah, I think this field is relatively well developed in terms of evaluation.
Okay, thanks.
And there is one more question in the chat. So could you please discuss spelling errors during the NEL?
Spelling errors, they might be affected by, they may affect candidate generation, and all, of course, depends how you perform this step. If you perform some kind of Levenstein distance, if you have spelling errors, I guess this is fine. If you rely on a set of predefined strings, and with such probabilities, and if the string contain error, well, it will be problematic to do. You can see, let's say here, if we take this development implementation, so they they use some matching is based on Levenstein distance between substring and entity title, right? So Levenstein distance might be, or something similar, is going to tackle to some extent this variation. Of course, if your data are very specific and from your very different from training data, you might want to do something special about it. Maybe try to resolve these errors beforehand. But yeah.
Okay, thank you. And there is another rather long question in the chat. Can you see it?
Oh, yeah, let me check. Yes. If you consider just a knowledge graph completion problem as a subpart of entity linking, what do you think about recent studies from ACL and HKI telling that almost all the models of knowledge graph embeddings are overfitting and not well generalized over other knowledge graphs? Okay, if we take just knowledge by graph embeddings, I guess if you take some models like TransE and DeepWalk, they are kind of overfitting by definition because they are just able to learn different vectors for given entity. They are not don't have any inductive properties at all. If you take something like graph convolutional networks, then they have these inductive properties, so they can deal with new entities. But yeah, so I'm a bit puzzled actually about the question. Because
Hi, Alexander. Maybe I'll just clarify the question. So basically, the problem is in following. So if you have a lot of entity relations, many knowledge graph embeddings models work quite well if these relations are somehow correlated in the data. And these studies tell something that in many data sets on which knowledge graph embeddings are verified, there are these correlations. And I mean, for the real world data sets, there may be no correlations between different entity relations, and in this way many knowledge graph embeddings should not work well in real world scenarios. So that's maybe the question that's interesting to discuss.
Yeah, but how this relates to entity linking, I'm not sure. You mean that? I'm still a bit puzzled. I mean, what is exactly? It might be so, but
yeah, when you are trying to connect something in knowledge graph, for example, such as knowledge graph completion, yeah, you also do something like entity linking. I mean, just from trying to link the data that were not explicitly, for example, extracted from the text using an NLP method when constructing knowledge graph, but then you try to use knowledge graph embeddings to link them. So I'm talking about this part.
Yeah, so when you do knowledge graph completion, the very common part with entity linking is this set of pre-trained entity representations, right? So basically what you have a graph, you go into encode the graph, you get a vector representation of every node, and then you are told like, hey, some links might be missing. How about creating links between nodes which are very close, let's say. Yeah, so and yeah, this is a kind of a machine learning problem, and they might be overfitting. But I cannot say really anything like specific about this in the context of neural interlinking, because other than the fact that representations for entity linking, they are quite they are like outsourced or taken usually from the research like you mentioned. So for entity linking, these entity representations, they might be obtained in the same way, but they are used kind of a very different way. Whether there is certain overfitting for these entities, I guess it's might be present, of course, but the question is how to measure this overfitting, to use domain-independent approaches to entity linking might be an answer to this question. If you have a new entity and if you have this kind of entity encoder which works well, then probably it's not overfitting. If your entity encoder is doing not so well, then I guess it's a better entity encoder.
I understand. Thank you.
Yeah. Okay.
Okay. So thank you. So maybe we have time for one very short question, if there is any. All right. So if there are no more questions, then thank you, Alexander, again. And thank you all for coming. So that's it for today. See you next time.
Thank you for having me. Bye-bye.